This video is a demonstration on the unit circle plate and how to use this activity to introduce the unit circle to students. What you'll need for this activity are a series of markers, a variety of colors, and then you'll need one paper plate per student. Ideally, these paper plates would have some kind of circular edge to them where it's not just fading, the perforation doesn't just fade into the plate itself like in this model, and it's maybe a bit flatter than this, because the flatter it is, the easier it will be for the students to be able to draw on it and create the lines that you're going to ask them to do. However, if you're not able to find something like that, like I wasn't, then just flatten these out as much as possible with the students, and then get them some rulers so that they have a straight edge to use. Okay, so first thing that we're going to do is a series of folds, and these folds are going to create the axes for our unit circle. So first fold I'm going to do is what we would have formerly called the hot dog fold. We're going to call it now the taco fold, since we're dealing with a circular piece of paper and it looks like a taco. So fold it taco style, flatten it out, then fold it again, and we'll call this fold quesadilla. So once you make your quesadilla, flatten it out as much as possible, create those creases, push down hard, open it back up. And now we've got a unit circle axes started. I'm going to take my darkest color here and trace my axes from the beginning of the inner circle all the way across the origin to about where the end of that inner circle is. Same thing on this axis, and you may need to fold it back in on itself so you can use the crease to make a solid straight line. Now, once you've done that, you're now going to fold it back into taco and back into quesadilla. And we're going to make one more additional fold in this regard, where we take it, fold it once more upon itself. We'll call this one the tortilla chip fold. This one's a little bit harder because of all the paper that you're trying to fold onto itself. But once you make it, go ahead and press down, open it back up. And now we've created the 45, 45, or 45 and then multiples of 45 all the way around angles for our unit circle. I'm going to take my next darkest color, which I have, which is blue, and trace from, again, the corner or the edge of the inner circle to the other edge as far as possible until that edge approaches. And same here. Okay. So now I've got my axes and my 45-degree angles. Now, from here we need to create the multiples of 30-degree angles, and these folds are a little bit more seemingly random, but not as random as you may think. You're going to take the bottom part of your plate, fold it upwards upon itself about halfway up towards the origin, and make a flat crease. You're going to repeat that on the upper and on the sides. So flat. Do that again over here. Flat. And once more. Flat. Alright, now, what you have now done is, where this circle is all the way across, you've now created creases that intersect with that circle. Take your next lightest pen or marker and put a point on the intersection of those creases with the edge of your circle. And it may be a little bit off. That's okay. Ideally, these should not be halfway in between the black lines and the blue lines. If so, the creases were not done correctly and shouldn't have been halfway in between. Because if they were halfway in between, then that would not be 30 degrees. That would be closer to the value of 45/2. So, now what we're going to do is, what your students should probably have is a straight edge at this point. I don't have one with me, so I'm just going to draw as straight of a line as I can from these points all the way to the origin, and then all the way out to that point on the other side. And from here, we're creating our 30-degree and multiples of 30-degree angles. Okay. And the last one. Okay, so we have all of our angles now. Our circle is this inner circle here. We have our axes. Let's go ahead and label these. I'm going to label my axes first. this is 0 degrees. I'm going to start labeling with radians because that's going to be the least common thing that students are used to at this point. They're used to degrees, not to radians. So in labeling my axes, I've got 0. My next axis is at 90 degrees, which is pi divided by 2. My next axis is at pi, so I've gone halfway around the circle, which has a circumference of 2 pi, since it is a unit circle with a radius length of 1. So this is pi. Another pi over 2 away, I get to 3 pi over 2, or 1.5 pi. Another pi over 2 away, I'm now at 2 pi. And I could continue going around and around and around, increasing my degree measure, or the other way, decreasing my degree measure, or my angle measure if I'm talking about radians. All right, so from here I'm going to label all my blue angles, which are in multiples of pi over 4. So starting with 0, I count up pi over 4. That's pi over 4 right there. Count another pi over 4, I'm at 2 pi over 4, which is at pi over 2. Another pi over 4, I get to 3 pi over 4. Another pi over 4, I get to 4 pi over 4, which is simplified already for me to pi. 4 pi over 4 plus pi over 4 is 5 pi over 4. 5 pi over 4 plus pi over 4 is 6 pi over 4, simplified to 3 pi over 2. 6 pi over 4 plus pi over 4 is 7 pi over 4. And 7 pi over 4 plus pi over 4 is 8 pi over 4, which is 2 pi. All right, next I'm going to label my green angles, which are in multiples of pi over 6. So we start at 0 and add pi over 6 to pi over 6. Add another pi over 6, I get to 2 pi over 6, which is simplified to pi over 3. 2 pi over 6 plus pi over 6 is 3 pi over 6. I already got that simplified to pi over 2. 3 pi over 6 plus pi over 6 is 4 pi over 6, which is 2 pi over 3 simplified. 4 pi over 6 plus 5 pi over 6 is 5 pi over 6. 5 pi over 6 plus pi over 6 is 6 pi over 6, which is pi. 6 pi over 6 plus pi over 6 is 7 pi over 6. 7 pi over 6 plus pi over 6 is 8 pi over 6, which is 4 pi over 3. 8 pi over 6 plus pi over 6 is 9 pi over 6, which is 3 pi over 2. 9 pi over 6 plus pi over 6 is 10 pi over 6, or 5 pi over 3. Pi over 6, or 10 pi over 6 plus pi over 6 is 11 pi over 6. And lastly, 11 pi over 6 plus pi over 6 is 12 pi over 6, which is 2 pi. So I've labeled now all of my angles. I'm now going to go through and label the coordinates of all of these angles. So I'm going to make sure that my angles have points at the end of them to represent that they are actually ordered pairs at the ends where they intersect with this circle, and that the coordinates themselves have some special meaning relating to the angle measures values for sine and cosine. So to construct these, I'm actually going to look at the 30, 60, 90 triangle relationship, and I'm going to use this 30, 60, 90 triangle right here. So I'm going to drop down that vertical. I'm going to label this right here as 30 degrees, or you could label it pi over 6, because that's what this is. And if you think about 30, 60, 90 triangles, the hypotenuse length was 2x. This leg that is adjacent to the 30 degree angle is x pi over 3, or x root 3. And then this leg that is opposite the 30 degree angle is x itself. Okay, so we said that this radius and all these radii all the way across are lengths of 1. So that means that 2x is 1. All right, so if I'm going to label the coordinates here, that's going to be x comma y. So x comma y. This length right here, if 2x is 1, that means that x itself is 1/2. So that means that this is 1/2 times root 3, which is root 3 over 2. And x is the y value in this case, which sounds a little confusing. X we said was 1/2, so x is 1/2 of this length. Is this leg length is 1/2, meaning the y value is 1/2. All right. Next, we've got labeling the 45, 45, 90 triangle. All right, so I'm going to drop down this vertical. I'm going to label this 45 degrees. All right, on the 45, 45, 90 triangle, x root 2 is the hypotenuse, and then x and x are the legs themselves, since the legs on an isosceles are the same. All right, so again, reminding ourselves that this radius is 1, that would mean that x has to be 1 over root 2 when I solve this for x. 1 over root 2 isn't that nice of a value. We like to rationalize that. So if I wrote that x is 1 over root 2, I can rationalize that by multiplying by root 2 over root 2, which tells me that x is really root 2 over 2. So x here and x here are both the length root 2 over 2. So that means that I'm going to label this coordinate root 2 over 2, root 2 over 2. Okay. All right. Let's now look at pi over 3. Pi over 3 is going to be very similar to pi over 6. The 30-degree angle on this is actually up here. So it's like I took this triangle and just flipped it. So that means I'm just going to take the coordinates and flip them. So 1/2 comma root 3 over 2. Okay. The easiest ones to think about are the axes, because if I have a length of 1 here and no movement on my y-axis, then I just went 1 comma 0. If the reverse is true, I went up but not left or right, then this is 0 comma 1. All right. So let's now expand this out to the entire rest of the unit circle. We know there's some symmetry here in this unit circle. So if this angle right here is root 3 over 2 1/2, then this angle right here is going to have the same values, root 3 over 2 1/2, except the x value will be negative since I went to the left of the y-axis here on the x-axis. So continuing that pattern down here, I have negative root 3 over 2, negative 1/2, and I have root 3 over 2, negative 1/2 here. Now let's look at pi over 3. Remember, it's going to be the same absolute values over here. So this will be a negative 1/2 positive root 3 over 2. Down here will be negative for both. And over here it'll be negative just for the y value. Let's look now at our pi over 4 values. So root 2 over 2, root 2 over 2, that'll be the same for all the coordinates, except some of them may be negative. Negative on the x over here. Negative on both down here. Negative only on the y over here. All right. And perhaps again the easier ones. Pi, we went one length over to the left, negative, but none up or down, so 0. And we went a length down, but not left or right. So 0, negative 1. All right, so what these values actually gave you were the sines and cosines of each of these angles. So if I'm looking for, say, the sine of pi over 6, well, one of these values is going to be the sine of pi over 6, but which? Okay, well, if I'm looking at the sine, remember that's opposite over hypotenuse. So opposite over hypotenuse, all right? So if I looked at this, x divided by 2x is going to leave me with 1 over 2. So that means that 1/2 is my sine value. All right. If I did the adjacent over hypotenuse, then that would be x root 3 over 2x. It's just going to leave me root 3 over 2, which is root 3 over 2. So it actually goes cosine, comma, sine. So each of these ordered pairs is actually the cosine, comma, sine of that angle. All right. So if I wanted to know what's the sine of pi over 2, it's 1. What is the cosine of 4 pi over 3? It's negative 1/2. Okay. All right. Additionally, it might be valuable for students to have on here the labels of the quadrants. So this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. I also like to have students label on here that quadrant 1, all trig values are positive. In quadrant 2, only sine and its reciprocal are positive. In quadrant 3, only tangent and its reciprocal are positive. And in quadrant 4, only cosine and its reciprocal are positive. So all students take calculus, all sine and its reciprocal, tangent and its reciprocal, cosine and its reciprocal. The last thing that might be valuable for you to show to students, not necessarily teach to students if they're not willing to use this as a trick for them to remember the values, is the left hand trick. The left-hand trick is only valuable once students understand where the values on the unit circle came from, and it's more of a memory device than it is a technique for knowing values. So the left hand is actually useful for remembering what these values are in the first quadrant of the unit circle, and then you can apply it to the other quadrants just by using the reference angles pi over 6, pi over 4, pi over 3 to figure out what the absolute values are, and then applying the negative where appropriate. So if I wanted to know what the cosine of pi over 6 is, then I use my left hand. Each of these fingers represents one of the 5 angles here on the unit circle. So this is 0, pi over 6, pi over 4, pi over 3, pi over 2. So if I want to know cosine of pi over 6, I close my pi over 6 angle. The cosine values are going to come from these fingers. The sine values are going to come from these fingers. Cosine, sine, just like on the unit circle. Okay? So cosine of pi over 6 is root 3 over 2. I get that because I have 1, 2, 3 fingers. So the square root of 3 fingers divided by 2. The sine value is the square root of 1 finger divided by 2. So it's the square root of your fingers over 2. So if I wanted to do pi over 3, then I close my pi over 3 finger. Pi over 3, if I wanted the sine of it, it goes cosine sine, so these 3 fingers, square root of 3 over 2. Square root of 3 over 2. It also works for tangent, and with tangent, you just have to remember you don't really need to divide by 2 because the 2's will divide out. If I wanted to know what the tangent of pi over 4 was, I close my pi over 4. I do sine over cosine. Well, that's square root of 2 over square root of 2, which is 1. So tangent of pi over 4 is 1. You're welcome to teach your students this device, this left-hand trick, to be able to remember the unit circle values. I feel like once they have been able to construct the unit circle, then it's valuable to show them an easier way to remember those values as they start to use them more and more in our trig units. This concludes your video and demonstration on the unit circle plate and the left-hand trick.